Welcome. In the next few videos, we're going to talk about some modifications to the ideal Rankine cycle, which make it closer to what is actually run in real power plants, like the James Turk plant that we talked about in class. So the first modification we're going to talk about is a subcooled condenser outlet. And essentially what this is doing is taking one of the modifications that was very important for coming up with the Rankine cycle initially, the fact that we can't pump a vapor-liquid mixture, and we're essentially modifying the system so that we for sure are not pumping a vapor-liquid mixture. So let's talk about what this would look like as a modification. So on a temperature entropy diagram, right, it's going to look essentially the same. So here's our boiler outlet. There's going to be a turbine down to there. Then this is the condenser, right? This is the condenser. And essentially what's happening in a traditional Rankine cycle, we're going right up to this point here. Where we have a saturated liquid, but that's kind of a tricky process, right? If we're designing actual equipment, it's hard to tell if we're going to get actually, right to this point here, or if we're going to accidentally end up somewhere like where I put that X. And that's a big difference actually functionally, because if we're where we have the X, we're going to be getting what we call bubbles or cavitation bubbles in the pump. Which is essentially steam bubbles. And those cavitation bubbles can lead to inefficiency. They also can lead to equipment failure. So our pump itself is going to deteriorate faster. It's going to be less efficient. That's going to cause some system failures. Functionally, it's really difficult to kind of tune your system so that you're getting to exactly a saturated liquid and you're not going a little short of that. So what we do instead is we cool down to here, right? So this is T-sat. This is T actual. We cool down to here, and this is a subcooled condenser outlet. Essentially what we're doing is we're saying, for example, let's say that the boiling point T-sat is 40 degrees Celsius. We're going to cool down to 35. Maybe something like that, a couple degrees below the saturated, so that we for sure are fully liquid. So this ensures that we're fully liquid. Then we could go up here, and then the rest of our system is going to look exactly the same. We're going to have this subcooled section here. And really a subcooled condenser outlet, right? Which by that I mean we're just below the boiling point. Ensures, I guess the best way to put it is it ensures consistent system operation. Right, it gives us kind of a buffer, if you want to think of it that way, for system variability. So if our condenser performance is changing a little bit, or our flow rates are changing a little bit, or the cooling water temperature is changing a little bit. By subcooling the condenser outlet, or designing our system to subcool the condenser outlet, as I've drawn there, it gives us just enough of a buffer that we can deal with slight changes in the operation without ending up with a situation where, you know, we're somewhere like that X that I drew there, where we end up with something that's not totally liquid, that's a vapor-liquid mixture, which would give us a number of different problems. So this is one way that we, just a practical limitation to be able to get more consistent system operation.